Systems are often built with stability in mind, yet many of them show a curious, almost paradoxical behavior. They seem to be in a perpetual state of reaction, constantly fighting fires. But if you look closer, their actions are always based on information that's no longer current. The result is a cycle of inefficiency and unpredictable outcomes. In this explainer, we're going to examine the underlying system structure that actually produces this pattern.
Now, you'd expect a self-correcting system to move smoothly towards its goal. When there's a problem, you anticipate a measured response that just, well, closes the gap. But the reality is often much more chaotic. Instead of a smooth adjustment, what you see is a pattern of wild oscillation, overshooting the target, then drastically overcorrecting in the other direction, creating this repeating cycle of instability. So to understand why this oscillation happens, we first have to look at how the system is supposed to work. At its core, it's designed as a goal-seeking mechanism, structured to maintain some kind of desired state. And the fundamental building block of any goal-seeking system is the balancing feedback loop. You can think of this as a self-regulating structure that works to minimize the difference between where a system wants to be and where it actually is. Its entire purpose is to counteract deviation and maintain a balance. The whole process kicks off when the system measures its current state and compares that to its goal. If there's a difference, a gap is perceived. This gap is really just the error that the system now needs to correct.
The existence of this gap immediately triggers a response. The system initiates some kind of corrective action, an intervention designed specifically to shrink that error and pull the actual state closer to the desired one.
And that corrective action, in turn, begins to alter the system's actual state. As the action takes hold, the condition of the system changes, moving it closer to the goal.
This change in the actual state is then fed back into the system, which remeasures and reevaluates the gap. This completes a kind of information circuit, where the output of the system constantly influences its future inputs. It allows for continuous self-adjustment.
So this structure seems perfectly logical, right? A gap is detected, an action is taken, the gap shrinks. On paper, this should lead to stable, controlled behavior. And yet, this collection of rational steps somehow produces a deeply irrational outcome, the overshooting and volatility we see in the real world. Something critical is clearly missing from our model.
The explanation for all this oscillation is found in an element that's inherent to just about every complex system, but it's often invisible in simple diagrams: time delay. This time delay is also known as latency. It's simply the interval between when an action is taken and when the full consequences of that action are actually felt and can be measured by the system. I mean, think about it. In almost any system of consequence, effects are rarely instantaneous. There is always an inherent lag between an action and its result. It just takes time for the full impact to ripple through the system and be measured.
So, what happens when we insert this time delay into our neat and tidy feedback loop? Well, the behavior of the entire system changes dramatically. It's no longer operating on real-time information.
The interaction between that goal-seeking balancing loop and this inherent time delay creates a dynamic that actively drives oscillation. It transforms a mechanism that was designed for stability into an engine of instability.
Let's trace how this happens, step by step. First, the system sees a big gap and, logically, initiates a strong corrective action. But here's the catch. Because of the delay, the effects aren't visible right away. The system looks again, sees the gap is still there, and thinks, my action isn't working enough, so it keeps applying pressure. Then, the full impact of all that cumulative action finally hits the system. By then, it's far too much. This overcorrection blows past the goal, creating a brand new gap, but in the opposite direction. And then the whole cycle starts all over again to correct this new error.
This resulting instability isn't a failure of any single component. No single decision is to blame. It's what's called an emergent property, a behavior that arises from the structure of the system itself. The oscillation is just a natural outcome of how the parts are connected.
As the control theorists Ostrom and Murray pointed out, trying to assign a single cause in a feedback system is a real problem. The relationships are circular and they're delayed. You have to look at the system as a whole. The issue isn't an isolated bad decision, it's the very structure of the loop.
The core problem that this delay creates is that the system is perpetually reacting to a state that no longer exists. All of its corrective actions are based on historical data, which makes them consistently mistimed for the present reality. It is always, quite literally, solving yesterday's problem.
And this leads to a fascinating paradox. Every single action the system takes is completely logical, based on the information it has at that moment. And yet, the sum of all these individually rational decisions, when you filter them through a time delay, produces a globally irrational outcome of cyclical instability and waste.
Now, this pattern of behavior isn't some rare anomaly. It's actually a well-understood structure in the field of system dynamics. It's known as a system archetype.
The structure is formally called the balancing loop with delay archetype. And it's a fundamental pattern you can find in countless domains, from supply chain management and economic cycles to biological populations and engineering control systems. It's everywhere.
And here's the key insight. The oscillating behavior isn't caused by the actors within the system making mistakes. Rather, it is a direct, unavoidable result of the system's design, of the feedback pathways and the inherent delays that are embedded within them.
Ultimately, this persistent cycle of overshoot and collapse reveals a foundational principle of systems thinking. A system's behavior is a direct reflection of its underlying structure. If you want to understand why a system performs the way it does, you have to look beyond individual events and actors, and instead focus on the feedback loops and delays that govern its operation.